Hello everyone, my name is Apoorv Bapat. I welcome you all to ELEATION's ANSYS Basic to Professional Training Program. Today, session 2, we are going to cover theory of FEM and CAE. We'll start with a recap that what we have seen in session 1. In session 1, we have discussed what is design validation, how many ways are there to validate any design, what is analytical, numerical and experimental method, how many numerical methods are there, what is finite element method, boundary element method, finite volume method and finite difference method, what is computer aided engineering and the difference between CAD and CAE. In today's session, we are going to see what is FEM, are FEA and FEM different, advantages of FEA and FEM, discretization of a problem, why do we carry out meshing, what is degree of freedom, element shape and its characteristics, 10 questions you should be able to answer. Let's start with what is FEA or FEM. Finite. Any continuous object has infinite degrees of freedom and it is not possible to solve the problem in this format. The finite element method reduces the degrees of freedom from infinite to finite with the help of discretization or meshing, or you can say via creating nodes and elements. All the calculations are made at limited number of points known as nodes. The entity joining nodes and forming a specific shape, say for example quadrilateral or triangular, is known as element. To get the value of variable, say displacement, anywhere in between the calculation point, an interpolation function as per the shape of element is used. Method. There are total 3 methods to solve any engineering problem. Finite element analysis or finite element method belongs to numerical method category. Let's take an example and understand FEM or FEA in more detail. So if I want to calculate the values of stresses on this plate, then actually this plate will have infinite number of calculation points. We as a CA engineer create some calculation points which are called as nodes. Then joining those calculation points, that is nodes, the software creates shapes which are called as elements. My software or any CA software calculates the values of stresses, strain, deformation on those calculation points which are called as nodes, and then with the help of interpolation functions show the result on entire domain or shows the result on the complete element. So this is the way FEM or FEA works. The biggest question is, are FEA and FEM different? So the answer to is finite element method and finite element analysis both are one and the same. The term FEA is more popular in industries while FEM is more popular at universities. Let's say some advantages of FEM and FEA. You have a better visualization of failure location, lower down the design cycle time, decrease the number of prototypes, cut the testing cost, and you can get optimum design in much lesser time. Let's see the discretization of a problem. All real life objects are continuous. This means there is no physical gap between any two consecutive particles. As per material science, any object is made up of small particles, particles of molecules, molecules of atoms, and so on. And they are bonded together by the force of attraction. Solving a real life problem with continuous material approach is difficult. The basis of all numerical method is to simplify the problem by discretizing, that is discontinuation. In other words, nodes work like atoms and with gap in between is filled by an entity called as element. Calculations are made at nodes and results are interpolated from the element. From a mechanical engineering point of view, any component or system can be represented by 3 basic elements, that is mass, spring and dampers. All numerical methods including finite element method follow a discrete approach. Meshing nodes and elements is nothing but discretization of continuous system with infinite degree of freedom to finite degree of freedom. Now let's understand why do we carry out meshing. The basic idea of FEA is to make calculation at only limited, that is finite number of points, and then interpolate the results for entire domain, or you can say surface or volume. Any continuous object has infinite degrees of freedom, and it's just not possible to solve the problem in this format. Finite element method reduces the degrees of freedom from infinite to finite with the help of discretization or meshing. The finite element method only makes calculation at limited number of points and then interpolate the results for entire domain. This is the reason why we carry out meshing. The next and the most important topic is what is degree of freedom. So the minimum number of parameters, that is motion, coordinate, temperature, etc. required to define the position of any entity completely in space is known as degree of freedom. In CAE world, there are total 6 degrees of freedom, that is 3 translational degrees of freedom and 3 rotational degrees of freedom. So you can fix a model in total 6 degrees of freedom. Let's take an example to understand how this degree of freedom concept works. Let's take a problem that two people are standing on ground, and the ground we are considering in the x-axis, and we ask one person to run in positive x-axis. Then we ask the other person to make him stop. If we want to make him stop, then he has to run either in negative x-axis or apply the same amount of force in negative x-axis. In the software world, instead of applying a force to counterbalance the actual loading condition, we can create a displacement in x-axis 0 for the first person. So if we have the displacement on x-axis 0 for the first person, then we can find the values of stresses and deformation on the string which is being produced because of the loading condition of the two people. So practically the situation is like this, where two people are applying force in opposite direction. In software world, we fix one position of a person and we apply force in another position of the person and find out the values of deformation and stresses. Based on degrees of freedom, you specify where to exactly apply the constraints and on what degrees of freedom you have to make that particular model fixed and free. We'll discuss this in detail as we go ahead of these sessions. So all of the elements do not always have 6 degrees of freedom. The number of degrees of freedom depends on type of element, that is 1D, 2D, 3D. The family of element, that is thin shell, plane stress, plane strain, membrane, etc. The type of analysis, for example, a structural analysis, a thin shell element has 6 degrees of freedom per node, displacement unknown and 3 translational and 3 rotational. While the same element when used for thermal analysis has single degree of freedom, temperature unknown. For a new user, it is a bit confusing, but there is a lot of logical, engineering and mathematical thinking behind assigning the specific number of degrees of freedom of different element types and families. So we are going to see in more detail about the degrees of freedom in further sessions. Let's start with the general procedure of CAE software. Let's assume we need to find axial stresses on any component. First, we have to find out the inertia of element. To find out the inertia of element, we need mass of that element. To know the mass of the element, we need density and volume. Density is a material property and volume is based on shape of the element. So once we have inertia on the element and then we apply load on that element, so we have original length of the element where the load is not applied. After applying the load, we know the change in length of that element. So if we have original length and change in length, then we can calculate strain. Once we know the strain and Young's modulus, we can calculate the stresses. So this is how my software works. So to know these values, you have to have a volume of the element. So volume for the element have to be calculated. Once you have the volume, you multiply with the software, multiply with its to density, generates the mass. Mass will have inertia. With the help of inertial effect, you can get change in length. With the help of change in length, you get strain, and with the help of strain and Young's modulus, you can find out stresses. Now we'll see what is element shapes and its characteristics. So in general, there are total 4 shapes possible: point, line, area and volume. A point element is typically defined as one node, such as mass element. A line element is typically represented by line connecting 2 or 3 nodes, for example beam, sphere, pipes, etc. We use 1D element or a line element when one of the dimension of the object or component is very large as compared to other two dimensions. An area element has a triangular or quadrilateral shape, for example chord and tria. We use 2D element when two of the dimension of the object or component is very large as compared to the third dimension, that generally it's a thickness. A volume element has a tetrahedral or a brick shape and is usually a 3D solid element. We use 3D element when all the three dimensions of the object or a component are comparable. Now let's understand how and what options we have to provide, or what additional parameters we have to provide and why we have to provide those. Let's take an example with 1D element. We use 1D element when the component length is very large as compared to the other two dimension, that is cross-sectional area. So let's consider a long steel rod. The length is too big and the cross-section is comparatively very small. So when we do 1D meshing, we create a line element. But as I already told you, we need volume. So line element will have length, but to get the volume, we need all the three dimensions. So additional parameter what we give to software is cross-sectional area. So my software multiplies that cross-sectional area with length and generates the volume. But my software will only give the results along the length. It will not give the results across the cross-section because there is no nodes across the cross-section. So if you want to find out the values of stresses and deformation of a steel rod across the cross-section, then you have to go for 3D meshing. With 1D meshing, you can only get the results along the length, not across the cross-section. But to generate volume, you have to give cross-sectional parameters. Similarly, for 2D elements, let's take an example of sheet metal component where the thickness is very less as compared to the other two dimensions. So once we do meshing, that is once we have 2D meshing on these types of components, we create area. Again, we don't have volume, so we give thickness. So thickness multiplied by area gives volume. And once we have volume, we can have mass, inertia effect and rest of the things. So my software gives answers on the area while you do 2D elements. It doesn't give you answers on the what is happening across the thickness. So if you want to get answers across the thickness, then again you have to go for 3D meshing. 3D element, let's consider a cube. You mesh it with either hexa element or a penta element or a tetra element. These all elements are 3D elements. They itself have a volume. They capture all the three dimensions. Nodes are available in all the three dimensions. So you get answers in all the three dimensions. So once you go for 3D meshing, you don't have to give any additional parameters to the software to convert that into volume, because that element itself is a volume. Now let's see the 10 questions which you should be able to answer before start any CAE simulation. The following is a list of 10 questions you should be able to answer about any given FE simulation, that is finite element simulation. It is also a good checklist to bring along to presentations by others as a guide to assure all your questions are answered. If you have not or cannot answer these questions, you need to go back and understand why. What is problem you are trying to solve, what geometry you are using, what solution type you are using, what is your material model, what are your element selections, what are your constraints, what are your loads, how you are combining the loads and constraints, what are the results, what are your recommendations. So we're going to answer all these questions in the next sessions. So as of now, I would like you to write on these points, and in the later sessions I'm going to explain you how and from where you get the answers of all these 10 questions. So thank you very much for attending session 2. In session 3, we are going to cover theory of 1D meshing, 1D element shape, when to use 1D elements, about deformation, axial stresses, bending stresses, difference between deformation, deflection and displacement, material properties like Young's modulus, Poisson's ratio and material density. If you have any queries or doubts, feel free to contact us via query@eleation.com, or you can visit www.eleation.com for more details. Thank you very much.